Now that we've explored sequences a little bit, let's look at a definition involving their behavior. We did mention this in class, but it's worth mentioning again. We say a sequence converges or is a convergent sequence if we can find a number L that we can make Sn, the terms of the sequence, as close to L as we want by making n large enough. So the way we write it is limit as n approaches infinity of S sub n is equal to L. Very similar to the behavior with functions as x goes to infinity. If, on the other hand, the sequence doesn't converge, meaning we can't find such a number L, then we say the sequence diverges. And as I mentioned in class, the possibilities for that include that the limit is infinity, negative infinity, or it just doesn't exist. And the doesn't exist usually involves some sort of oscillation that happens in a way that doesn't seem to land on anything. So the idea of a sequence having a limit as n goes to infinity is the same as the idea of a continuous function having a limit as x goes to infinity. The only difference is sequences are discrete, functions are continuous. This is essentially the answer to the previous activity that we were talking about. Now let's look at some examples. This activity is saying use graphical, so something like Desmos, and or algebraic methods, which is saying your prior knowledge about how to calculate certain limits could be involved to determine whether each of the following sequences converges or diverges. You look at something like part A, there's two ways to approach it. As the instructions say, we could either graph it using something like Desmos and make an educated guess about what it approaches, or we could think of this as limit as n goes to infinity of 1 plus 2n over 3n minus 2. And we could pretend that the n here is actually an x, because what we're trying to say here is that taking the limit of a sequence as n goes to infinity is similar to and going to give us the same result as when we take the limit as x goes to infinity of a continuous function. So think about the techniques you would use to calculate a limit like this. Quick hint, when you have the limit of a rational function as n goes to infinity, it's often helpful to multiply top and bottom of this rational function by 1 over the highest power of the variable you see. So that's your hint for that one. For part B, we have the sequence 5 plus 3 to the n over 10 plus 2 to the n. Now that one will probably end up, if we try to set up a limit similar to how we did in part A, we'll probably end up with something like infinity over infinity. So consider what type of technique we use for a limit that we learned in this class, where you would deal with something that has an infinity over infinity appearance at the beginning. Try that, see how that works. We'll talk about it in class if you are still stuck. And maybe that's not even the right initial approach, but I'm just giving you a starting point here. Part C is the one I want to give you the most help with right now, because it's going to involve something very different from what you've worked with before. It says 10 to the n over n factorial is the formula that gives us each term in this sequence. You may or may not have seen this exclamation point. It's factorial. So we say n factorial. We don't say n. And n factorial means n times n minus 1 times n minus 2, all the way down till you get to 1. So for example, if I write 1 factorial, that's just 1 because I'm already at 1. 2 factorial would be 2 times 1. 3 factorial would be 3 times 2 times 1, etc. It says here that we define as a convention 0 factorial to be 1, but there's actually a mathematical reason behind that. It's because this factorial, another way to think of it is it's the number of ways of arranging that many things. For example, if I have 2 things and I want to think about the ways to arrange them, say I have a square and a circle, I can either arrange it as square circle or circle square, right? That's my 2 ways of arranging that. But for something else, if I have 3 objects, let's say diamond, square, circle, how many different ways are there to arrange this? Well, I could switch around the circle and the square, or I could have the square at the beginning and then the diamond and the circle after that. And then once I do that, I can actually switch the circle and the diamond. Or I could start with the circle and then have the diamond followed by the square. And keeping the circle first, I could switch the square and the diamond. And this would be every single possible way to arrange 3 things in a given order. So then why does that imply that 0 factorial should be 1? Well, think about it. If you have 0 things, how many ways are there to arrange those 0 things? Well, there's just 0 things in front of you. There's only 1 way to arrange that. All right, now that we've talked about what factorial means, let's actually figure out a strategy to answer a question like this. So my hint for this is to consider the following. Let's say you have different n values that you plug in to try to understand how this function behaves. So you have, for n equals 1, it would be 10 to the 1 over 1 factorial. For n equals 2, you'd have 10 squared over 2 factorial, and so on. Let's say you consider 10 to the 6th over 6 factorial. That would be when n equals 6. And then let's skip, let's say when we have 10, n equals 10, we have 10 to the 10 over 10 factorial. Let's examine this one real quick. If we write it out, we have 10 times 10 times 10, 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then underneath we have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So a hint for number activity 1.4 part C is to consider what is going on here. What is this approaching, if it's approaching anything? Or is it growing without bound? So consider playing with different terms. Maybe you'll even want to go to higher values of n and see if you can find any patterns. Another thing you can do is you can compare terms. So this term compares with a similar term in what other sequence? So that's another thing to consider.